Okay, let's get started. So welcome everyone to another lecture in our ID 5130 Parallel Scientific Computing course. Okay, so we kind of pretty much finished the MPI programming function calls and the way MPI works and things like that, except for one last thing in the chapter, that is basically the performance evaluation and analysis. Okay, so we are going to look at performance evaluation and or performance analysis in today's lecture, in which we are essentially going to introduce some metrics with which we can kind of measure the parallel performance of a particular program that we write, okay, or even a particular algorithm for that matter. Okay, so essentially so the idea is that we have to know when it is kind of whether a particular algorithm is amenable to parallelization, or is it cost effective for parallelization or not. So essentially sometimes we kind of come across some of the tools, some tools like such as, let's say, parallelization, that we like them so much that we will use them even in the cases when they are actually not needed. So essentially we have to not only learn to design and parallelize algorithms, and in addition we should also know when to use these parallel, when to use parallelization. For example, some of the algorithms are programs or algorithms are kind of amenable to parallelizations, and some of them are not. Okay, so it is as important to know and learn what are the costs and benefits associated with parallelization, or running a program in parallel, as important as to know these costs and benefits associated with the parallelization, as to know essentially how to parallelize. So basically both are important. So we should also kind of emphasize on that one should know when to parallelize them. So in today's lecture we're going to look at basically we will kind of know or understand how much a particular program, how much faster a parallel program may run when compared to a serial program. Okay, we will also know how to predict the parallel performance. So we will also learn how to predict the parallel performance of a given algorithm. Okay, so essentially to this end we will be learning, introducing few new keywords or definitions, and those are basically speed up and then efficiency, and we are also going to look at something that is known as Amdahl's law and Amdahl's effect. Okay, so this is all we are going to kind of learn. There are a few more things which I will mention towards the end of the lecture, which we are not going to learn, but they may be useful later on when you try to do a project or something like that. Okay, all right, so let's get started. So in order to know how much faster a parallel program performs compared to a serial program, we use the first metric, that is known as the speed up. Okay, so basically speed up by definition is or speed up of an algorithm is kind of a measure of how much faster a parallel program runs than a sequential algorithm. Okay, than its sequential counterpart. Okay, so essentially, if you were to define speedup as a ratio of, let's say, the execution times, then speedup can be written as the ratio of the sequential execution time or execution time of the serial code upon the parallel execution time. Okay. Okay, so that is the definition. So that means we can always, if you have a particular serial code and a parallel code, you can always run these two codes and then find out what is the speedup, right? Of course, you may think, okay, would I not know the speedup? In general, would I not know the speedup until I run it? But let's say if your algorithm has several iterations, then you could probably perform, instead of performing all the iterations, you could perform a few iterations and measure this, and then you can kind of come up with the speed up for your program. Okay, of course you can also see if that is valid over by changing the number of iterations you have considered, so that you get the correct ballpark number for your speed up. Okay, so when you come to the sequential execution time, it's kind of very straightforward, because this is the time it's taken by the serial code or the sequential code, whereas when it comes to the parallel execution time, the parallel execution time in the parallel algorithm can be kind of decomposed into three main components. Okay, so essentially the parallel algorithm has three primary components. Right, so the first one is basically, so the parallel algorithm might have some part of the algorithm that inherently needs to be run in a sequential manner. So basically you would probably have an inherently sequential part of the computation, right? Say for example, you have to read from a user or write to a particular file and things like that. So those are all kind of sequential activities, and they need to be run or ought to be run in serial or in sequential manner, even in a parallel environment. Okay, so that is the first component. The second component is, of course, the main component is the parallelizable part of the algorithm. That is the parallelizable, right, part of the computation, which we hope is the basically your main essentially the algorithm, main part of the algorithm or program that kind of can be run in parallel, right? Okay, so this is I mean, because of the existence of this, we have taken the task of parallelizing a particular code. Okay, all right, then the third part is of course the overhead that is associated in the parallel algorithm, right? So overhead that is associated with the parallel algorithm, which is otherwise absent in the serial algorithm, right? Right, so essentially out of these three, what we realize is that the sequential part and the parallelizable part, these are also there in the serial algorithm as well. Only thing is that the parallel part also will be run in serial, whereas the overhead that is there, this is associated only with the parallel algorithm, and this is not there in the serial part of the algorithm. Okay, so that's what we realize. All right, and then of course the overhead that we're talking about here can be again further talked about into three components or or more. So we can talk about essentially communication overhead, right? So in the context of MPI, communication overhead can be thought of as your MPI send receive or any other collective communications and things like that, right? Essentially the time or the work associated with sending and receiving the data across the process. And the second one is, of course, the creation of the processes themselves, creation, right, of the process themselves. That is basically in the context of MPI, you are saying that you are calling MPI initialize, and then you are calling MPI finalize and things like that. Or in the context of OpenMP, you have basically forking and joining, right? So these are all the overheads associated with the creation of the threads or the processes itself. And then of course you also have something that is basically redundant, right? So you have some redundant computations that you would perform, which can be kind of thought of as overhead computation or time in the parallel algorithm. Again, this would not be there in the serial algorithm because there is only one process. So there could be some redundant computations. For example, let's say you have to calculate a local h or something, and the local h needs to be computed in every or the step size h in the context of, let's say, our trapezoidal rule needs to be computed in every process. So this is kind of a redundant computation, but of course part of it is even done in parallel. Okay, so that is that could probably add to some overhead in the parallel algorithm. Okay, all right. So in order to so far we have kind of defined all these things, but then in order to proceed, in order to perform some kind of quantitative analysis, so in order to perform some quantitative analysis, we are going to now associate the what we call as the computation that we are referring to, right, or the computation or the work that we are associating. We are going to do this, we will kind of make this an abstract concept, and we say that this, when we talk about computation or work for a particular program, either it is serial or parallel, we are going to say that all these three components that we talked about can be measured synonymously using some kind of time units. Okay, so that means when we say parallel program performs some computation, then we say that it basically performs it basically consumes some time units, and that is what we will use synonymous with the computation or work. Okay, that means if we go back and say that the inherently sequential part of the computation is let's say if it is, say, s, then what we say is that s is basically some s seconds or something is the inherently sequential part of the computation. Okay, similarly, if we say the parallelizable part of the computation is some let's say some p, then we say that this is p seconds is basically the parallelizable part of the computation. Okay, so that's basically associated with some kind of time. Okay, so it means we are going to use the computation and time interchangeably. Okay, so that we can talk about computation and time interchangeably, so that we can kind of come up with some quantitative analysis. Okay, so let us introduce some kind of notation to denote the these three components that are there in the parallel algorithm, which is basically the inherently sequential part of the algorithm of the computation, and then the parallelizable part of the computation, and the overheads that is associated with the parallel algorithm. Okay, so that means, and we are also going to define a few variables here. So let me call sigma n as the sequential part of the computation, right, of the parallel algorithm, and then as we write here, sigma is basically, this is some time unit, some 10 seconds or few seconds, or or few hours or whatever, but then again it's basically a function of n, and where n is the problem size. For example, in the context of matrix, let's say n could be if you have an m by m matrix, your n could be probably m square or something like this. Okay, fine. Or you could even take m as your n if you are going to define m as your problem size. Okay, but you understand that wherever you say m, you are actually talking about one dimension of the matrix, but not the m square. Okay, all right. Then we would also introduce another symbol, another notation for the parallelizable part of the algorithm. That is, let's call it as a phi of n. So this is basically part of the computation that may be executed in parallel, right? that may be executed in parallel. And again, we see that this is basically it kind of depends on the problem size, that is basically n, right? So as your problem size n grows, the phi of n also might grow. Basically, it kind of depends on how much part of the computation can be made into parallel. Okay. All right. Then you have the overheads. Let us define overheads using kappa k, and then let us also say that it's basically a function of, not only a function of the problem size but also of the number of processes. Okay. So this is the problem size and p is the number of processes. Okay, that means kappa n as a function of np, because as the number of processes increases, the amount of computation, amount of overhead also kind of increases, right? Because depending on, if you have 2 processes, only they have to communicate. If you have 10 processes, then I think all the 10 have to kind of communicate. So as a result, your overhead increases, right? And also the overhead of creating the processes and destroying them, these all will add it up to the overheads here. Okay, so that means this is basically the parallel overhead of the computation. That is associated with a problem size n and the number of process p. Okay. All right. Now let us see if we can define speed up using these variables or notations we have introduced. Okay. So let us also have a symbol for speed up. Let us call it psi of np as the speed up achieved by by a particular essentially by a particular program or a parallel program, by solving a problem of size n on p number of processes. Okay, by solving a problem of size n on p process, right? Okay, so let us see now if we can define psi of np using these 3 variables that we have introduced. Okay, so let us first talk about basically the speed up is now defined as sequential time to the parallel execution time. So we have the sequential execution time here to the ratio of parallel execution time. So let us calculate what is the sequential execution time using these notation that we have introduced. Okay, so that means the sequential execution time can be written as basically the sigma n, that is the sequential part of the computation, or inherently sequential part of the computation, of course, needs to be done by the sequential program as well. And then you have the parallel part of the computation that may be run in parallel, but because we are running a serial program, it will be run in serial. Okay, so it will be run in serial, so as a result it will be run as phi of n seconds will be taken by it. Okay, so let's call this as the sequential execution time. Then what about the parallel execution time? The parallel execution time would be equal to, of course, the parallel algorithm still has to run the sequential part of the algorithm in series or sequence, right? So that means sigma n will still be there, and then of course you have the parallel part of the algorithm, and then the parallel part of the algorithm could be run in parallel, so it would take, depending on the number of process, phi n by p, right? It will only take phi n by p time, because this will be shared by all the p process, so it will be phi n by p, plus you have the communication overheads, that is basically, or the overheads which are associated with the communication or redundancy as well as creation and destruction of the process. So you have kappa of np, right? So this is the total parallel execution time. Okay, that means we can now easily define our speed up from these 2 definitions, right, of the sequential execution time to the parallel execution time ratio. However, before we do that, let us kind of little bit think about this particular term here, phi n by p. Now this phi n by p basically tells us that the inherently or the parallelizable part of the computation can be run by pre-process, and this is basically done in this is basically an ideal way, right? That means all of them will split the work, and then they can just do it by phi n by p in a time of phi n by p. However, this is kind of the ideal, right? So this is basically the if you end up distributing this n uniformly across all the processes, then all the process would be able to do it this way. Otherwise, it will be, the time taken would be greater than phi n by p, right? Because one process might be getting more number of points, or it might have to wait for a while, or things like that, depending on the algorithm. So that means this is the best possible, right, parallel execution time, right? Execution time. That means this is the best possible, meaning this is the least amount of time that the parallel algorithm consumes, right? So that means if it is not ideal, the time executed will be larger than this, right? Now, because this is now occurring in the denominator in the definition of speed up, that means the speed up achieved by using these two definitions would be the maximum speed up that you would get, and otherwise the speed up would be less than what is predicted by these definitions, because now phi n by p may not be the best split in a particular algorithm. Okay, so as a result, now we can define speed up shy of np, noting that this is the maximum speed up, and the speed up would be less than or equal to, right, whatever is given. So this is the ratio of sequential execution time, that is sigma n plus phi n divided by the parallel execution, that is sigma n plus phi n upon p plus kappa of np, right? Now we realize that because if this is the best, this is the maximum you can get, but otherwise the speed up you would get would be always less than this value, right? So this is the maximum speed up that you can obtain from your program. And if you analyze your program for the sequential part and for the parallel execution, the part of the program that can be run in parallel, and if you know these things, you could always calculate what is psi of np, right, which will give you the maximum speed up possible. Now, at a first look, it may appear that the speed up, as we kind of, if on any particular problem, if we can keep increasing the number of processes, if we keep increasing process, it may appear that the speed up kind of increases, but that is not correct, because as we keep increasing the p, your phi n by p of course goes down. However, the other component, that is the overhead part of the computation, this could have been better here, okay, the overhead part of the computation here, right, k of np, this would actually the k of np would actually increase as you keep increasing the number of processes. So essentially, as a result, you would not get a maximum speed up as you keep throwing more and more process at your for your algorithm or for your program. Rather, what you get is there is an optimum point at which the decrease in phi n by p is kind of offset by the kn of p. As a result, there is an optimum number of processes, okay, for any optimum number of p exist for a given problem size n, that would basically maximize the speed up. Okay, so that is the takeaway message from this definition of speed up. Okay, all right, now let us so essentially as we kind of keep increasing p, the speed up does not increase proportionately. As a result, the number of processes are kind of being wasted. Okay, so we need to that means if you write a program, you cannot just run it on some 10,000 processes or 20,000 processes and so on, thinking that you would get maximum speed up or your algorithm would finish quickly. Rather, it may so happen that your algorithm would take longer than what it would have actually taken on a less number of processes. Okay, so that is kind of very important to know. Fine, that means so far so good. So we have now introduced the definition of speed up. So before we go into the efficiency, let us talk about let us say if you have to let's say purchase or ask for some computational power or some computational time on a particular machine. It could be on Aqua or any other machine. Let's say you're writing a proposal and you have to kind of give the amount of computational time that you would need to run your simulations, right? You may say I would probably need let's say 30 cores of for, let's say, for 24 hours a day, for, let's say, you would need it for a month to run your simulation or something like this. Or you may say, okay, I would like to have maybe 100 cores or something, and then eventually you would kind of convert this into number of core hours, right? And then you would put in there in your proposal, and then the granting agency, if they find merit, they would basically give you these many hours of computational time on a particular process, on a particular machine, and you will be able to run it. Now, how would you decide how many processes you have to actually use for your particular program, and so on? So this is where you cannot just give as large a number as possible here, because as we have just discussed, if you give a large number of processes, most of the time on the cluster or on the big machine would be spent in the communications, right? Because the K of NP would be larger rather than in the actual computations. Okay, most of the time would be spent in communication rather than in the actual computation. That means rather than in the phi of n, most of the time would be spent by kappa of np. As a result, your program not only runs slower, you will be wasting a lot of resources. So as a result, this is not a good way to do. So we have to kind of measure whether it is whether your program is efficient or not, and that is where we kind of define the next metric, that is basically the efficiency, which is a measure of the processor utilization. Okay, so this is kind of very closely connected to the speed up, as we will see it. So efficiency also will be a function of the problem size as well as the number of processes. And if you were to denote efficiency using epsilon of as a function of problem size and the number of processes, so we can define efficiency as the sequential execution time upon the parallel execution time times the number of processes. That means this is very much related to the speed up. We just have to divide your speed up by the number of processes, right? Because the sequential execution time to the parallel execution time is already defined as a psi of np. We just need to divide psi of np by p to get the efficiency, right? That means if you were to use the definition of psi of np, which we have just now defined here, so I would use psi of np equals less than or equal to sigma n plus Vn upon sigma n plus Vn by p plus kappa of np. I can write what is the maximum efficiency that is possible would be less than or equal to sigma n plus phi of n would be better, phi of n divided by p times sigma n plus phi n by p plus kappa of np, right? Okay, so that's what we have. Now of course this can be simplified by multiplying with p. So efficiency for n and p can be written as p times sigma n plus phi of n plus p times kappa of np. Okay, all right. We can also of course now define limits, because all these quantities are kind of positive. The communication overhead will be greater than or equal to 0. Similarly, this is greater than or equal to 0, and then the sequential part is greater than or equal to 0. So this is always kind of greater than or equal to 0. So your efficiency of np would be always positive, and as your p goes to infinity, right, this basically goes to 0, right? May go to 0, or essentially we can talk about p equals 1, right? If you have a single process, then the communication time is basically, there is no communication overhead. So this is equal to 0, and then p equals 1. This becomes sigma n plus Vn by sigma n plus Vn. So this is 1. So the maximum possible efficiency you can get is basically 1. So efficiency would kind of range from 0 to 1. Okay. All right. So now using this definition, you could say whether you are for a particular program, if you can measure what is your sigma n, phi n, and the communication overheads in some way, then you could always define the efficiency, and then you could kind of calculate this, right? Now, of course, this is one way to do it. Other ways to do it is directly measure it. Like you could probably run your program for a certain number of iterations, and you could say that for a given problem size and the number of process, you could kind of time your program and then define sequential execution time divided by parallel execution time times the number of process, and that would basically give you what is your efficiency for a given problem size on a particular number of process that is used, and then you can map and accordingly decide with what efficiency you could probably ask for the how many hours you want and things like that. Okay, so that is where efficiency would come kind of handy. All right, now we have kind of briefly touched upon this idea where we said that kind of putting in more processes is not going to speed up your program, right? So we kind of briefly looked at that, saying that essentially your kappa of NP would actually increase. That means the overhead associated with your parallel program would increase, and that is what would kind of will not allow for increase in speed up, right? Although your phi n by p kind of decreases. Okay, so this is what was actually kind of argued or by Amdahl back in 1967, and which came out to be known as Amdahl's law. Okay, so about 1960s, 1970s, Amdahl, who worked at IBM, he kind of argued that there is an inherent limitation limit or limitation to the amount of speed up that could be obtained by performing computations using more number of processes. That means even if you want to put in more and more number of processes, your speed up would not increase, right? Your speed up is kind of limited, and that is what is kind of argued by Amdahl, and later it kind of came to be known as Amdahl's law. Okay, so what Amdahl or later on it was kind of proposed or put in a better form than what was suggested by Amdahl by other researchers. And then if we say that using a different notation, now I'm using little f here to denote the fraction of operations in a computation, the fraction of operations in a computation that must be performed in serial, just a second here. Okay, if f is the fraction of operations in a computation that must be performed in serial, right, or in sequentially, that means f can range from 0 to 1, where if f is 0, that means there are no operations that can be performed sequentially. That means it's completely parallelizable, and f equals 1 means you cannot essentially parallelize any parts of the computation, right, or the algorithm that you have. So defining f as this the fraction of operations in a computation that must be performed in serial or sequentially, then the maximum speed up according to Amdahl, the maximum speed up achievable or obtainable by a parallel program running on pre-processors is basically given by psi equals 1 by f plus 1 minus f divided by p. Okay, so as you can see, as p tends to infinite, your psi tends to 1 upon f, right? So that means there is inherently a restriction on the maximum speed up that can be obtained even if you keep taking your more and more number of processes. According to Amdahl, the maximum speed up that can be obtained is only inverse of the sequential part of the computation that we have in the code. Okay, so the more inherently sequential part of the computation in the algorithm, the more less would be the speed up that is possible, right? So that means yeah, so for any so essentially we already know that if you have a fixed problem size, that means for you have a fixed n, then what we know is that essentially for this particular problem we know that the essentially sequential part of the computation is fixed, right? This is basically fixed. But what Amdahl's law says is that if you have a problem of fixed size, it is not only the sequential part but also the maximum speed up, essentially the upper bound on the speed up is also fixed. So it means psi of n is also fixed, right? For any number of process, right? Or for the process that can be used. Okay, so how do we kind of connect this with the previous definition that we have? We can easily do that. We just have to start off with the previous definition. The previous definition for speed up was sigma n plus phi of n divided by sigma n plus phi of n divided by p plus kappa of np, right? All right, now of course in Amdahl's law, the parallel overhead is basically always greater than or equal to 0. That means we can now define, of course this was less than or equal to, because this is not ideal. The distribution of the parallelizable part is not ideal, right? So that means what we can say is that this, because this is always greater than or equal to 0, this entire thing would be less than without this part, right? So that means we can say that psi of np, which is defined as sigma n plus phi of n divided by sigma n plus phi of n divided by p times kappa of np. This will always be less than or equal to sigma n plus phi of n divided by sigma n plus phi of n divided by p, and I'm not writing the k of np, I'm not writing the overhead part, right? And then now we would be using this particular definition for the speed up, and then you already can relate the sequential fraction of the part of the computations as sigma n divided by sigma n plus phi of n, right? So earlier sigma n is the sequential part of the computation, whereas f is the fraction of computations that must be performed in serial. Okay, so this is slightly different. This is fraction of computations that needs to be performed in serial. Okay, that means I am dividing the amount of the sequential part divided by is kind of divided with the total work, right, or the total time needs to be performed in serial. Okay, all right. So having said that, now I can of course now relate f equals sigma n by sigma n plus phi of n. Then of course we would need sigma n plus phi of n. So I can write sigma n plus phi of n from here as 1 upon f times sigma n, right? So that can be written. Then we can also write what is phi of n in terms of sigma n. So phi of n in terms of sigma n would be sigma n times 1 upon f minus 1, right? We can write that. That means I can go back to this definition, psi of np equals sigma n plus phi of n divided by sigma n plus phi of n divided by p. Now I can substitute for these quantities. Sigma n plus phi of n equals 1 upon f sigma n divided by sigma n plus 1 by p times phi of n. We just wrote it as sigma n times 1 by f minus 1, right? Now if you simplify this, you can kind of cancel sigma n as well as p remains the same, and then you can write it as f plus 1 minus f divided by p, right? That's what you would get as psi of np. Okay, so that's nothing but your Amdahl's law. Okay, all right. So far so good. That means if we have, let's say, if in your algorithm you know that if the fraction of the computation that needs to be executed in serial is, let's say, is about 10%, right? Then you can plug in, if you were to use maximum of 10 processes, then you can plug in f equals 0.1, p equals 10, and calculate what is the maximum speed up possible for this problem, right? You can calculate this as psi to be less than or equal to 1 by 0.1 plus 10 times 0.9, right? That's basically 1 by right, this is 10 processes, and then you have divided by 10, right? So this is basically 0.9 divided by 10, so 0.09, and then you have 0.19. So that means your maximum speed up you could get psi would be less than or equal to 1 by 0.19, which will come out to be approximately 5. Okay, all right, so that we could kind of calculate. So this is no matter, so essentially if you use 10 process, this is the maximum speed up that can be achieved using Amdahl's law. If you have if 10% of your is the fraction of the time that needs to be spent in serial. Okay, all right, so that's so far so good. Now let us look at a few more consequences of the Amdahl's law. Consequences of Amdahl's law. Okay, all right, so we can say that in general the sequential part of the computation is usually kind of linear with respect to the problem size, because for example the sequential part usually will be the reading and writing IO part. So this can be kind of treated as kind of linear with respect to the n. That means we could say that the sequential part is proportional to n, or we could even come up with some kind of a model for the sequential part. So let us say sigma n equals sum a n plus b. So as the problem size increases, your sequential part of the computation also increases, and it only increases linearly. And let us also come up with some estimate for our number of computations that can be performed in parallel for a particular problem. And usually, let's say if you have let's say a sorting algorithm or something like that, we basically have around order n square operations, right? Or if you have matrix multiplication, you have order n cube and things like that. Let me take order n square. So let me model phi of n to be equal to some constant c times n square. Okay, so this is basically the parallelizable part of the algorithm. This is the parallelizable part of the algorithm. Okay, now we have to of course come up with, now that's all you need to kind of need a model for sigma n and need a model for phi of n, so that you could actually calculate what is your f, right? Your f in the in here you would need sigma n and phi of n. You don't actually need a k of np, because this is kind of ignored in Amdahl's law, right? So we would not need a model for this. We will see that later on, but as of now let us see, using this you can calculate what is the sequential fraction, and then you can calculate the psi, right? So let me do that, but then before I do that, we need to give some kind of values for this a, b and c, and it is kind of, let us say, usually the computations are basically the mathematical operations or the floating point operations, right? These usually occur in at least in microseconds or in nanoseconds and things like that, whereas the IO operations, which are reading from the user or reading from a file, all these things usually happen in terms of milliseconds. So that means if I were to denote let's say a and b using 100 microseconds and maybe b using 1000 microseconds, that means around a millisecond and a 0.1 millisecond, and let us denote c to be equal to maybe a quarter of a microsecond. Okay, that means 0.25 times microseconds. Then we could write what is sigma n. This is basically your 100 n plus 1000, right? And similarly your phi of n can be written as 0.25 times n square, and this is now in microseconds, and this is microseconds. Okay, then you could calculate what is f as a function of n, right? F of n can be calculated. Once you know f of n, and given a particular problem size p, or given a particular number of processes, right, we could calculate what is the maximum or what is the speed up, right? What is the maximum speed up attainable for this particular algorithm, right? Now I have some algorithm for which I have defined the sequential part of the computation and the parallel part of the computations. Okay, now of course, if you can do this, that means you're going to get you basically define f equals sigma n divided by sigma n plus v of n, basically plug in these relations, and then you calculate what is psi from 1 by f plus 1 minus f times divided by p. Okay, then we could actually plot as a function of n or p, or for a given problem size n, we could plot psi as a function of number of process, right? So, and then analyze how does this work as you keep increasing process, what will happen to the speed up, right, for this particular problem, right? We could do that, and then we could do that for different n, right? That means we could do it for different problem sizes. Okay, so that is what I set out to do next. So what I do is I would just basically write a small GNU plot script, right, which I would show it here. Okay, so what I have here is basically you can ignore these statements. These are related to basically creating the file and things like that. So I have a equals 100, b equals 1000, c equals 0.25. That is basically the same as what I have written here, right, in microseconds. And then we have n equals 5000. So I'm testing it for two different n. This is the first n, this is the second n, and then the first n I kind of use a trailing 1 to denote f1 case 1, and then for all 2 I use a trailing 2 here. So for if you have a problem size of 5000 points, you're calculating sigma of n equals an plus b and phi of n equals cn square, and then f1 is basically sigma by sigma n plus phi of n, and then your psi for a given problem size n, it's only a function of number of process. So psi of 1 of p equals 1 by f plus 1 minus f by p. Okay, similarly I repeat the same code here for 10,000 points, 10,000 problem size, and sigma 2 equals an plus b, and phi 2 equals cn square, and f2 equals sigma 2 by sigma 2 plus phi of 2, right? And then you have psi of p equals 1 by f plus 1 minus f divided by p. Okay, then I just put in some labels here. X-axis is number of process, y-axis is the speed up, maximum speed up actually, right? Maximum speed up. Then I just plot it using this command, right? So basically I'm using 20 process. Oops. I'm using 20 process. Okay, and then I just plot these two values. Okay, let me run this and see. Okay, GNU Amdahl speed of graph. So it basically ran, and it will give me the graph as an EPS file. It is here. So on the x-axis we have number of process going from 1 to 20. On the y-axis I have the maximum speed up. So what we see is that for 5000 points, which is problem size, as I keep increasing the number of process, according to Amdahl's law, we are getting this particular speed up, right? So it's kind of saturating, and then as you increase the problem size, the speed up you can obtain is more, right? Basically that means according to Amdahl's law, if you for a fixed number of processes, if you are working with a larger problem size, the speed up attainable will be larger. That is because on a larger problem size, your sequential fraction f is actually smaller. Okay, so that is the reason. That means what we notice from here is that for a fixed number of processes, the speed up, maximum speed up obtained is larger for a larger problem size. Okay, that means what we can also say this in a different way. For a fixed number of processes, the psi max is larger for larger n because
the sequential fraction of the code is actually smaller for the larger problem size. Okay, so that is why essentially the psi max comes out to be larger, because you have 1 by f plus 1 minus f divided by p, and f effectively becomes smaller because your sigma n and phi n are kind of grow in such a way that your f kind of tends to be smaller as your n increases, right? And that's why your kind of speed up comes out to be larger according to Amdahl's law. Okay, so far so good. Now what we realize is that this is fine, but what we realize is that Amdahl's law does not actually take into account the communication overhead, or it doesn't take into account the k of np, right? Is not considered in Amdahl's law, right? So now can we include this and analyze? Can we include this and analyze? Yes, we can, of course. Only thing is that we need to, of course, now kind of make some model of how k of np varies with respect to the function of n comma p. If we can come up with a functional form for this, then we can certainly include this and use the speed up definition that we have used from the definition, right? And then we could calculate what is the speed up by including the overhead, right, from the definition, by including the overhead, and then we could actually compute what is psi of np. Okay, so to do that, let me kind of introduce, let me kind of say that if we have, let's say, in a particular computation or a particular algorithm, let us say there are log n points or log n locations where we need to communicate. Log n locations in the code, right, or log n times we need to communicate between the processes. Now each communication of course takes some time, and let us introduce a model for the communication cost as this thing. Let us say each computation now kind of takes about 10 to the 4 ceiling of log p, right, plus n upon 10. Let us say this is the approximate model, okay, for each communication cost. That means it kind of is a function of the number of, is a problem size as well as number of process you have. So this is a model for each communication cost, and then we have log n ceiling. So this is basically rounded off to the next integer, and this is also ceiling, and then and this is the total computational time consumed by the overheads is basically multiplication of number of locations times the number of computations we have per location. Okay, that means we can use these two. That means we can write our k of np to be equal to log n ceiling times 10 to the 4 log p plus n upon 10 microseconds. Okay, so that is our k of np. Now we have already introduced a model for sigma 1, which is equal to a n plus b, and we have introduced a model for our phi of n, that is basically cn square. Now we have all of these things, then we can of course just go ahead and calculate what is psi of np to be by definition sigma n plus phi of n divided by sigma n plus phi of n divided by p times kappa of np. Okay, so let us try to do that in a different program. Of course, we need to now fix n. So we are going to see the effect of the overhead. So for that, I will have another program, a small script here in GNU plot. So this, again, these things are the same as before. We have 1000, 100, 1000 and 0.25, and now I fix the problem set equal to 5000. So for 5000 points, that means we are again focusing on this cross symbols here. Now with Amdahl's law, we got around 8.2 or something, right, as the maximum speed up at 20 process. Now this curve is going to remain the same, and we're going to see what is actually the realistic curve that we would obtain if you include the overheads in the calculation of the speed up, right? So this is basically the maximum speed up. Now I am calculating. So sigma 1, this basically stands for the maximum speed up, right? So this is the maximum speed up, right, proposed by Amdahl, right? That is what is maximum proposed by Amdahl. And then now we are looking at actual speed up obtained by including the overheads, right? Okay, so what are the overheads? Overheads is basically kappa of n comma p. N is already fixed, so it's only a function of p. That's basically log n times 10 to the 4 log p plus n by 10. Okay, and then we have sigma 2 is sigma n is a n plus b, phi n is c n square, and then psi is now from the by definition from first principles we have sigma n plus phi divided by sigma n plus phi n by p plus kappa of p. Okay, and then I plot both of them. No overheads is basically the first one, and with overheads the second one. Okay, so I would just run this program. I would close this thing, but we will basically get this curve again. Okay, anyway, I'll keep it maybe required. So I run the overheads program. It ran and wrote this particular overheads. Okay, so now what we see is that this is basically your 5000 quantity. Now it's kind of reset it to be 8. Okay, and then what we see is that with overheads the speed up has come down to substantially to around 6.4 or 2 or something like that, right? So that means with overheads we see that the speed up that is proposed by Amdahl has come down, because this is the realistic speed up that can be achieved by including the overheads into the picture. Okay, so that means what we can say is that a couple of things we can say about the overheads is that the k of np is usually has a smaller complexity than, so we can say inclusion of k of np provides realistic psi of np values, and these psi of np will be less than or equal to psi of np max that was proposed by Amdahl. And then we can also say that the complexity of k of np has a complexity smaller than your computation. That means k of np would not be, for example, phi of n was basically on the order of n square. K of np would never be so large, right? If it is so large, we would never go for kind of distributed memory programming. So this is always has a smaller complexity as a function of n. So as a result, as a consequence of this, as the problem size increases, okay, as the problem size increases for a fixed number of processes, okay, the maximum possible speed up tends to increase. So what we say is that basically your k of np has a smaller complexity. As a result, as your for a fixed number of processes, as you keep your p, as you keep increasing your n, your phi of n, which is basically the parallelizable part, will become smaller and smaller. As a result, your speed up, maximum possible speed up or actual speed up, would actually tends to increase as you increase the problem size. Okay, so and this particular statement is known as Amdahl's effect. Okay, that means for a fixed number of processes, if you increase your problem size, your maximum possible speed up is going to increase. Okay, all right, so that is one thing. And then there are of course a lot of other metrics that are proposed in the literature. Those are known as the, other than the Amdahl's law, there is also something that is known as the Gustafson and Barsis law. There is also something that is known as Cart-Flat metric, and there is something else known as iso-efficiency relation. We are kind of not going into all these details towards this particular class, but if you are interested you can kind of read upon them. But however, I feel that the speed up and efficiency should be sufficient for you to use when you try to do your project, in order to kind of measure your performance of the parallel program that you would write. Okay, so with that I'm going to kind of stop here, and that kind of finishes the programming in MPI chapter. And in the next lecture we are going to kind of start off with numerical methods in MPI. Okay, I'm going to stop here. Thank you.